Quantum entanglement, famously described by Albert Einstein as spooky action at a distance, has long fascinated physicists and sparked imaginations worldwide. This strange quantum phenomenon occurs when two or more particles become deeply interconnected, regardless of the distance separating them. Measuring the state of one particle instantaneously determines the state of its entangled partner, even if they are separated by vast distances. Over recent decades, entanglement has emerged as the cornerstone of quantum computing, cryptography, and communications. But recently, researchers have begun to pose a more radical question. Could entanglement facilitate information transfer not just across space, but across different points in time? The idea of transferring information through time, even in principle, challenges established notions of causality and linearity. Yet quantum physics, with its counterintuitive principles, provides a fertile ground for exploring such daring possibilities. Recent experiments and theoretical proposals have begun to demonstrate that entanglement might indeed play a critical role in the temporal dimension, potentially enabling quantum states and information to connect events across time, at least in simulated quantum environments. The concept of temporal entanglement stems from the idea that quantum correlations could exist not only spatially, but temporally, connecting quantum states across different moments in time. Physicists have coined terms like quantum temporal correlations and entanglement in time to describe these fascinating phenomena. Rather than entangling two particles separated by physical distance, temporal entanglement considers correlations between the same particle's quantum states at different moments. In practice, exploring temporal entanglement involves carefully designed quantum simulations. Researchers use advanced quantum computing simulators and quantum optical systems to create controlled environments where quantum states are prepared, manipulated, and measured at distinct points in simulated time. By carefully encoding information into initial quantum states and then measuring them at later points, physicists can study how entanglement might preserve or transfer quantum information through temporal intervals. One groundbreaking study, published by researchers at prestigious quantum research institutes, has demonstrated compelling evidence that entangled quantum states can indeed transmit information across simulated temporal intervals. In these quantum simulations, physicists prepared quantum bits, qubits, in carefully constructed, entangled states. They then introduced artificial temporal gaps using computational and experimental protocols that mimic the passage of time. Remarkably, the quantum states successfully carried encoded information across these simulated intervals without significant loss or distortion of the original quantum information. This result, though preliminary and conducted in carefully controlled simulations, carries profound implications. First and foremost, it suggests that quantum entanglement might indeed provide a pathway for information to transcend conventional temporal constraints. If these findings hold up under further rigorous experimental scrutiny, they could fundamentally alter how we conceive of quantum communication and information transfer. Practically speaking, leveraging temporal entanglement could revolutionize secure quantum communication protocols. Current quantum cryptographic methods rely heavily on spatial entanglement to secure information transmission, ensuring that any interception attempt inevitably disturbs the quantum states and alerts the communicating parties. Introducing temporal entanglement into these protocols could potentially provide additional layers of security and robustness, enabling quantum information to be securely stored and transmitted through time intervals, not just across distance. Moreover, the possibility of temporal entanglement invites physicists and information theorists to revisit foundational concepts of causality and information flow. Quantum mechanics already pushes at the boundaries of classical intuition, but temporal entanglement would represent a deeper shift. If quantum states can indeed correlate across different points in time, researchers may need to rethink classical assumptions about causation, linearity, and temporality itself. This naturally leads to speculative yet intriguing implications for ideas commonly associated with time travel. While it is critical to emphasize that these quantum experiments do not demonstrate or even directly imply macroscopic time travel, they do raise compelling theoretical questions. Could quantum information transmitted backward through simulated time intervals provide insights into resolving classical temporal paradoxes? Could quantum entanglement and temporal correlations offer new theoretical frameworks for understanding time travel scenarios, even if only at the microscopic quantum scale? Physicists approaching these questions remain cautious, fully aware of the speculative leap from quantum information transfer in simulations to actual physical time travel. Nonetheless, the theoretical curiosity and excitement generated by temporal entanglement studies have revitalized discussions about time, causality, and the fundamental structure of quantum communication. Yet, significant scientific and philosophical challenges remain. One primary hurdle is the issue of causality violation. If information could indeed be transmitted backward in real physical time, it could theoretically enable paradoxes such as the well-known grandfather paradox, in which an effect precedes its cause. Many physicists suspect that nature inherently forbids such scenarios through unknown quantum or cosmological principles. Thus, further research into temporal entanglement could also help illuminate nature's intrinsic safeguards against paradoxes and causality violations. Future research directions will likely focus on expanding these initial experiments from simulations to real-world quantum systems. Physicists are already developing sophisticated quantum hardware capable of more precisely manipulating and measuring quantum states over extended temporal intervals. Additionally, interdisciplinary collaboration between quantum physicists, information theorists, philosophers, and cosmologists will be crucial in exploring and contextualizing these groundbreaking findings. In conclusion, the emerging study of quantum entanglement's role in temporal information transfer represents an exciting and provocative frontier in quantum physics. While still in early stages, these novel experiments and theoretical explorations challenge conventional wisdom, inspire fresh thinking about fundamental concepts, and point toward potentially transformative technological applications. Whether or not actual information transfer through physical time proves feasible, continued research into quantum temporal entanglement promises to deepen our understanding of quantum mechanics, redefine concepts of causality, and perhaps even illuminate possibilities currently residing only within the bounds of imagination.